we will be doing several examples in which we are solving logarithmic equations. Just like with solving all equations, for the most part, we will be working from the outside in, undoing mathematical operations until we have solved for our variable. That is, gotten our variable all by itself on one side of the equal sign. Our first example is the natural log of 5x squared equals 5. Remember, natural log is log base e, and log functions are the inverses of exponential functions. So the very first thing we need to undo is this natural log function. So I need to plug the natural log function into an exponential function with base e. So I write down the expression e raised to the natural log of 5x squared. I am actually plugging natural log in as the exponent on an exponential function base e. The two inverse functions will cancel each other out, leaving me with the 5x squared that was plugged into the log function. Now notice, whatever I do to one side, I have to do the same thing to the other side. So the 5 also has to get plugged in as an input to an exponential function with base e. So on the right hand side, I will have e raised to the 5th power. So I've now done step 1. I've simplified my equation so that I have 5x squared equals e to the 5th. I still don't have x by itself, so I keep working from the outside in. I'm going to divide both sides by 5. That gives me x squared equals e to the 5th divided by 5. Now I need to undo the square. So undoing the square, I will take the square root of both sides. Remember, when you undo an even power, what was being squared could have been positive or could have been negative. Hence, when I take the square root, I have to acknowledge that x, or what was being squared, could have been positive or could have been negative. So I have two solutions: positive square root of e to the 5th over 5 and negative square root of e to the 5th over 5. That is the exact solutions. E is an irrational number. There is no decimal expansion that's exactly equal to e, so any decimal I write down is going to be an approximation. The square root of 5 is also irrational, and it's involved in my answer. So if I wanted the exact answer, I should just leave it as positive or negative square root of e to the 5th over 5. If you look at our graph, we have the graph of ln of 5x squared, and it has two sections. One is negative on the negative side of the x-axis, and one's on the positive side of the x-axis. And notice we have two solutions where it's crossing the horizontal line y equals 5. One of the solutions is the square root of e to the 5th over 5, approximately 5.448, and the other solution is negative square root of e to the 5th over 5, or approximately negative 5.448. So we can see from our graph that we have two solutions. The exact values are positive or negative square root of e to the 5th over 5, or approximately positive or negative 5.448. Now sometimes with equations, you actually need to adjust the form before you can actually get to the steps where you are undoing the mathematical operations to get at your variable. Notice here my variable is showing up many locations throughout my equation. I have log base 2 of 6x plus 1 minus log base 2 of 1/2 x equals log base 2 of 4x. So the x is showing up in different places. So I need to try to condense the equation to eventually isolate the variable. We'll use our rules of logarithms that we learned in the earlier section to rewrite this equation to help us get an expression that will allow us to solve for our variable. Remember from our rules of logarithms, log base b of a minus log base b of c is equivalent to log base b of a divided by c. I can divide the first input by the second input. So I'm going to do that with the left-hand side of the equation and condense it down so I have a single log expression on the left-hand side. Again, I'm able to do that because of the rules of logarithms that kind of work in concert with the rules of exponents. So that will clean up then as log base 2 of 12x plus 2 in the numerator and x in the denominator. Remember, dividing is the same as multiplying by the reciprocal. So dividing by x over 2 is equivalent to multiplying by 2 over x. Hence, when I multiply by 2 in the numerator, I get 6 times 2 is 12, so I get 12x, and then 1 times 2 is 2. On the right-hand side, at the moment, I'm just leaving it as log base 2 of 4x. I still have the variable in several locations in my equation, but I now have log base 2 of an expression equals log base 2 of an expression. So I need to undo the log base 2. Hence, I need to use its inverse function. Exponential base 2 is the inverse of log base 2. So the log base 2 functions need to be used as inputs to exponential functions with base 2. So I take both sides of the equation, because remember, whatever you do to one side, you have to do the same thing to the other side to keep it balanced. You plug the log expressions with base 2 into exponential functions base 2. So the logs are now exponents with a base of 2. So the base 2 exponent functions cancel the log base 2 functions, and I am left with 12x plus 2 divided by x on the left and 4x on the right. The log base 2's got canceled by the exponential base 2's. But notice, because both the left and the right sides of the equations involved log base 2, I could just reason out, you know what, the input of the log base 2 on the left has to match the input of the log base 2 on the right, otherwise those two expressions won't be equal. So really, you could kind of skip my step where I'm plugging them into exponential base 2, because we know that the expression inside of the log on the left has to equal the expression of the log on the right. And so you could just jump right away to recognizing that 12x plus 2 divided by x needs to equal 4x. Okay, so we had our original equation, log base 2 of 6x plus 1 minus log base 2 of 1/2 x equals log base 2 of 4x. And we used our rules of logarithms to rewrite the expression on the left so that it was log base 2 of 6x plus 1 divided by the 1/2 x, giving us 12x plus 2 divided by x equals 4x. Now we are needing to solve this equation. I'm going to multiply both sides by x to cancel out the denominator. That leaves me with 12x plus 2 equals 4x squared, and I have a quadratic equation. So if I rearrange things so that 0 is on one side of the equal sign and all of the other terms are on the other side of the equal sign, I can solve this by normal methods that you use to solve quadratic equations. Those methods are either do completing the square and then undo the steps to get x by itself, factoring, or quadratic equation. I'm going to use the quadratic equation. So my linear term is -12, my leading coefficient is 4, and my constant is -2. So plugging that in, we take the opposite of the linear term, so minus -12, and then you add or subtract the square root of the linear term squared, so -12 squared, minus 4 times the leading coefficient, which happens to also be 4, times the constant, -2, and then you divide by 2 times the leading coefficient. So that gives me 12 plus or minus the square root of 12 squared minus 4 times negative 2. Notice when you are squaring, it doesn't really matter if you put the negative in or not, but if you're not squaring, be careful with those negatives. They do make a difference in the final value. Cleaning up the quadratic equation, I get positive 12 plus or minus the square root of 176, and that is divided by 8 because 2 times the leading coefficient was 8. Notice 12 is even and 8 is even, and also 176 has a perfect square as a factor, and it is a perfect square of 16, so I can factor 4 out of the square root of 176, and reducing, I then get 3 plus or minus the square root of 11, because 11 is the other factor after you divide 176 by 16, and 8 divided by 4 is 2. So 12 was divided by 4, and again, in 176, there was a factor of 16, but when you take the square root of that, you get a 4. You were left with the square root of 11, and then the denominator was 8, so 8 divided by 4 is 2. Now that gives me 2 possible solutions. One is approximately 3.1583, and the other one is approximately negative 0.1583 when I actually subtract the square root of 11 from 3 and divide by 2. But we started with a logarithmic equation, and log functions are not defined for negative values. So if I tried to plug negative 0.1583 into the log base 2 of 1/2 x expression or the log base 2 of 4x expression, I would be trying to plug an undefined negative value into those log expressions. So we're going to ignore the second solution of negative 0.1583, and the only solution is positive 3.1583. Notice when we do graph the left and right hand sides of the original equation, we can see that we get one solution in which x is approximately 3.1583. The red graph is log base 2 of 6x plus 1 minus log base 2 of 1/2 x, and that's the graph that's kind of coming down from infinity and flattening out a little bit lower than 4. And the log base 2 of 4x graph is the one that's coming up from negative infinity, and you can see that the two graphs cross over each other at one point, and the x coordinate of that point is approximately 3.1583. Many situations that could be modeled with exponential functions can also be modeled with log functions, because logs are the inverse functions of exponential functions, and you can just rewrite the functions using their inverses. From basically rewriting it from the perspective of the inverse function. Here we have a exponential decay problem rewritten as a log equation, and we are trying to solve for the proportion of an element I-123 remaining, and I-123 has a decay rate of 5.251%. 5.5 hours have passed since a sample was first taken. So notice I have a number, 5.5 times negative 0.05251, equal to natural log of our variable p, where p is the proportion of this element remaining. If we multiply 5.5 by negative 0.05251, we get approximately negative 0.288805, and that is set equal to natural log of p. P is our variable, it is inside a log function. So an exponential function needs to be used to cancel out the log function. ln means log base e. So an exponential function base e is going to be the exponential function that will be the inverse. So both sides of the equation will get used as an exponent on a base of e. because what you are basically doing is plugging it into an exponential function that is its inverse. So the e and the natural log cancel each other out like inverse functions do, and you solve for your variable p. So then p is equal to e to the negative 0.28805, and we can probably approximate that number, giving us an estimate of the proportion of this element that is remaining. E to the negative 0.28805 is approximately 0.7492, and you can also interpret that as 74.92%. So after 5.5 hours, approximately 75% or 74.92% of this element remains. There are several formulas that can be used to measure the strength or magnitude of an earthquake. The most famous is the Richter Scale, but over time that formula has been tweaked to give what some people think is a better measure of the intensity of an earthquake. In this formula, d is the distance from the epicenter and a is the maximum ground displacement of the p waves in micrometers. So m equals log base 10 of a plus 1.6 log base 10 of d minus 0.15. Suppose that an epicenter is 150 kilometers away, and we want to solve for the maximum ground displacement of the p waves if m is 7.6. Plugging the appropriate values in, we then get the equation 7.6 equals log base 10 of a, which is the variable we're trying to solve for, plus 1.6 log base 10 of 150 minus 0.15. Remember, solving equations involves undoing all the mathematical operations until you get your variable isolated. In this case, let's first collect like terms. So the negative 0.15 can be added to the 7.6. So I add 0.15 to cancel subtracting 0.15. And whatever I do to one side, I do the same thing to the other side. So that gives us 7.75. I can then subtract the log term, 1.6 log base 10 of 150, because that expression is really just a number. I know it kind of looks like it's a function, but it has a value plugged into it. And so the 7.75 is a constant, the 1.6 log base 10 of 150 is a constant. So I'm putting all of the constants together on one side of the equation and leaving the variable part, log base 10 of a, on the other side of the equation. So now I've basically isolated the log base 10 of a, which is the function part of our equation, or the variable part of our equation. It is a log base 10 expression, so I need the inverse of a log base 10 expression. So exponential base 10 is the inverse of log base 10. So I'm going to plug the log base 10 of a into exponential base 10. And when I do that, I'm plugging log base 10 into its inverse. But whatever I do to one side, I have to do the same thing to the other side. Hence, I'm going to take the left-hand side and also use it as an input on an exponential base 10, just like I did on the right-hand side. So on the right-hand side, the base 10 exponential function cancels the base 10 log function, giving me a. And on the right-hand side, I can use some of the rules of exponents to clean it up. Remember, when you are multiplying exponents and the bases are the same, you can add the exponents. So I'm working that rule of exponents backwards. I really have 7.75 plus negative 0.16 log base 10 of 150. So I can break that up as 10 to the 7.75 times 10 to the negative 1.6 log base 10 of 150. And that is equal to our variable a. The reason why I want to bother trying to rewrite a, I mean, I've actually solved for a, but With the rules of exponents and rules of logs, we can probably clean up that value a little bit. So remember, a negative exponent is defined to be the reciprocal, so I can rewrite the left-hand side as 10 to the 7.75 being divided by, because the idea of the reciprocal, 10 to the 1.6 log base 10 of 150. Again, that is what A equals, but we can keep using our rules of logs and rules of exponents to clean this up. One of the rules of logarithms says that the leading coefficient of a log is actually an exponent on the input of the log. So that 1.6, that's a leading coefficient of log base 10 of 150, can be used as the exponent on a base of 150. And then I can notice that I have 10 to the log base 10, and 10 to the log base 10 cancels because they're inverse functions, and I end up with 10 to the 7.75 being divided by 150 to the 1.6. So writing that down is actually cleaner than any of our other versions of our solution for A, and you can approximate that to be 18,546.16 micrometers. A micrometer is a millionth of a meter. And so with this earthquake of magnitude 7.6, 150 kilometers from the epicenter, the P waves had a maximum displacement of 0.01854616 approximately as the measure in meters. Newton's law of cooling is another famous application of exponential logarithmic functions that can be written in exponential form or in logarithmic form. Here we have an example written in logarithmic form. Suppose a glaze for cookies is heated to 220 degrees Fahrenheit and the room has a constant temperature of 68 degrees Fahrenheit. We want to solve the following equation for the current temperature of the glaze after 45 minutes. 45 minutes is 3/4 of an hour, or 0.75. So that's equal to -4 times natural log of T, which is going to be the current temperature, minus 68, which was the temperature of the environment, divided by 220, our original temperature of the glaze, minus, again, 68. So again, it's 0.75 equals -4 times natural log plugged inside of the natural log is T minus 68 divided by 220 minus 68. Newton's law of cooling is another example of a type of equation that can be written in an exponential form or a logarithmic form. Here we have an example in the logarithmic form. Suppose a glaze for cookies is heated to 220 degrees Fahrenheit and the environment is 68 degrees Fahrenheit. We want to solve for the current temperature, T, after 45 minutes. 45 minutes is 3/4 of an hour. So we have 0.75 equals -4. Now the -4 is relative to the substance that is cooling, and that is multiplying natural log of the rational expression T minus 68 divided by 220 minus 68. Notice 68 is the temperature of the environment, the room. 220 is the original temperature of the substance. Working from the inside out, we want to first divide by 4. So when I divide by 4, I get -0.1875, and that's set equal to the natural log of T minus 68 over 220 minus 68. Then I need to undo the log function. So the log function needs to be used as the input to an exponential function with matching base. So ln is base e, so I'm going to use exponential base e. So both sides of the equation, remember what you do to one side, you have to do the same thing to the other side. So both sides get plugged in as the exponent on an exponential base e. With the log expression, the exponential cancels the log. and otherwise e to the negative 0.1875 is just a constant that we will use in our solution. So when we cancel out the log function, we end up with our input of t minus 68 being divided by 220 minus 68. 220 minus 68 is 152. So we have the constant e to the negative 0.1875 equals the variable expression t minus 68 divided by 152. We're still trying to solve for our variables. We want to cancel out the division by 152 by multiplying. So e to the negative 0.1875 should get multiplied by the 152 because I need to multiply both sides of the equation by the same thing. And so on the right-hand side, multiplying by 152 cancels the dividing by 152, leaving me with t minus 68. Then lastly, if I add 68, I will cancel the subtraction of 68. So I get e to the negative 0.1875 times 152 plus 68 is equal to the time that I am looking for. If you correctly type that expression into a calculator, you will see that e to the negative 0.1875 times 152 plus 68 is approximately 194 degrees Fahrenheit. So after 45 minutes, the glaze has cooled from 220 degrees Fahrenheit to 194 degrees Fahrenheit in a room which had an environmental temperature of 68 degrees. Functions can be used to model objects. For example, we might be wanting to make a container like a compost bin, and it will have a cross-section given by y equals natural log of 3x minus 42 times x minus 32. A wide parabola that opens to the right will serve as the lid, and it'll fit snugly into the top of our container. In order for the specifications to be what is desired, those two curves need to intersect at y equals 6.5 inches. That then gives us the equation 6.5 equals natural log of 3x minus 42 times x minus 32. Again, the parabola is part of the overall design, but at the moment we're trying to find what value of x is going to make the other part of the curve that actually forms the container equal to 6.5. Solving this equation, we want to undo the natural log function. So natural logs are the inverses of exponential. Once again, we have natural log, so its base is e. So I need to use the natural log as an exponent on base e. I'm plugging it into an exponential base e function, and whatever I do to one side, I have to do the same thing to the other side. And so that gives me e to the 6.5 is equal to e to the natural log of our input expression 3x minus 42 times x minus 32. The exponential functions cancel each other out. That gives me e to the 6.5, which is some constant, equal to what was plugged into the natural log, 3x minus 42 times x minus 32, what was plugged into the natural log. If I FOIL out or multiply out 3x minus 42 times x minus 32, 3x times x is x squared, 3x times negative 32 added to negative 42 times x gives me a middle linear term of negative 138x, and negative 42 times negative 32 is positive 1,344. So I have this constant, e to the 6.5. It is some number set equal to 3x squared minus 138x plus 1,344. Now, this is a messy quadratic equation, and the way we normally solve messy quadratic equations is with the quadratic formula. But for the quadratic formula to work accurately or to be true, I need it set equal to 0. The quadratic formula is used to find the zeros of a quadratic equation, so I can't have my quadratic set equal to e to the 6.5 it's actually not going to do its job. So I need to subtract e to the 6.5 from both sides and kind of group it with the 1,344 because both of those are the constants. And then I would be able to use the quadratic formula. So the quadratic formula is always the same. You take the opposite of the b or the linear term and you add or subtract the square root of b squared minus 4 times a times c divided by 2 times a, where a is a leading coefficient and c is the constant and b is the middle linear term. So I'm going to follow that even though I have kind of messy numbers. Numbers are just numbers. So I have 138 plus or minus the square root of 138 squared minus 4 times 3, because that's my leading coefficient, and my constant is the 1,344 minus e to the 6.5. That entire thing should be then divided by 2 times a. If I carefully plug all that in my calculator, I get two solutions. One is approximately 5.6 inches, and the other one is a number that in the context of the problem is not really going to make sense. So the only value that makes sense, because we're talking about a solution near the top of the container, is x is approximately 5.6. So at 5.6 inches in the cross section, the lid will be tapering in and hitting the edge of the container.